Hello, everyone. My name is Feng Fu. So today is my great pleasure to present my work in class mechanism of space structure under fair conditions. So let's look at the background. As we all see that there are so many fair incidents across the world. For instance, in UK alone, between 2016 to 2017, there was 161,000 fair incidents. And among them, there are about 261 fire-related fatalities and about 7,000 non-fatal casualties in fire. So therefore, we can say that the fire safety is crucial in construction projects. However, if we look at, so nowadays, so many research studies have been focused on the fire safety for buildings, and field study has been done on long-span space structures. So let me quickly introduce about the space structure. Space structure has been widely used for the long-span roof. For instance, like Wembley stadiums, and also some like power stations, and also like Olympic stadiums, and also like stations such as Concourse station. So they have many kinds, different types. So primarily, we have two types of space structure. We call that double layer grids. So that's very common. So I believe you must have seen that. So double layer grids are one of the most popular space structures. They have a flat surface and consist of a top and bottom layer. And also they have diagonal web members. Another main type of space structure is the latticed shells. So they can either be double layer or single layer. In latticed shell, the joints, the major difference between the double layer grid and also latticed shell is that in the latticed shell, the joints are normally detailed in such a way that they can resist internal moment and torsion, as well as axial loading. But for the double layer grid, we normally design the pin support for the connection so that they only can take axial load. So that's the difference between them. But however, for a double layer grid, due to its great redundancy, and compared to the single layer shell, the joint can be designed as pinned. Yeah, so occasionally they can also be designed as pinned. So that's the two main type of the space structures. So they do have some like fair incidents in those space structures, but no research has been done so far. So this my research is primarily focused on the single layer latticed shells. So let's look at the feature for single layer latticed shell. So due to the inherent curvatures, yeah, latticed shell provide greater stiffness than other type of space structure. And also, if you're using a single layer lattice shell, so they can also reduce the weight. So therefore, the cost, yeah, because in the space structure, the cost primarily comes from the tonnage of the steel members. So if you can save the weight, you can save the cost. That's quite important. So single layer lattice grids are usually composed of smaller span members as larger span members are most likely to buckle due to the compressive axial force. So that's the advantage of using the single layer lattice shells. So nowadays the shell structure are designed with more complex geometric shapes. You know, sometimes, for instance, like a hyperbolic shells, or sometimes even a very unique shape, as I'm going to introduce, like a Concourse station roof. But the class mechanism of this type of structure under fire is unknown because no one has ever investigated. So the objective of the research in this presentation is primarily to investigate the behavior of single-layer lattice shell under fire conditions, study the class mechanism of a single-layer lattice shell under fire conditions, and also develop an effective way to set up an accurate 3D finite element model to model the single layer grid with a complicated geometry, because the geometry is so complex, so it's difficult to model. So we provide a new way to model that effectively. I'm going to introduce later. And also for sure, we want to know the thermal response and the thermomechanical response. So we want to perform coupled thermomechanical analysis for single layer lattice shell. So now let's look at the prototype structure. We particularly select King Cross Station Western Concourse roof due to the complexity of this roof. So the Western Concourse roof consists of very complex geometry, and it is a semicircular single-layer grid shell dome structure consists of a rectangular hollow section and also some of CHS circular hollow sections. So this is a photo I took like a long time ago when I was waiting for the train in King Cross Station. We can see the shape are so complicated, yeah. So like the curvature here, yeah. So how do we model that effectively? That's become very challenging job for us. So I'm going to introduce how do we do that. So if you look at my book, so probably someone know my name because I published several books, so including one book is quite popular called Advanced Modeling Techniques in Structure Design. I particularly introduce how do we model the complex structures. Yeah. So that book is primarily based on my experience when I was working in WSP group. I worked as a key member. I work for the advanced analysis team, so we have done so many fantastic structures. So most of that are very like complicated. So that book primarily introduced how are we going to model those complex structures. What I normally do is that I build up a so-called wireframe model. So the wireframe means you only have lines to represent the structure member. You don't model anything else. You don't model the thickness. You don't model the sections. Yeah. So normally you can do that in a draft software. See, for instance, like AutoCAD or Rhino. So let's look at that. Yeah. So this is what we did in AutoCAD. So it's a 3D model, 3D representation for the King Cross Station roof. So we can look at here. So this is the dome itself, and also it support in some of the column at the perimeter in the circumference. And then in the center is supported on a truss. We call that a truss column. So we model first in a 3D model in AutoCAD. Yeah, we model the geometry because you can't do that in any finite element program because it's too difficult, like Abacus and ANSYS. And then later on, what you can do is you can directly import them into ANSYS or Abacus, but you can also define the section. As I said, it's wireframe, but you can also define the section here in AutoCAD, but that depends on the ability of the your finite element software, whether it can define the section easily, because ANSYS is not that good in define the section. It's very difficult, to be honest. So what we did is that we define the cross section directly in AutoCAD, and then we import into ANSYS. So this is after the import into the ANSYS. So the full dome has been imported into the ANSYS. Yeah. And then we are going to do some, first we're going to set up some like a fair temperature, like we call that the atmosphere temperature, or we call that room temperature. So we can using parametric fair temperature, but here to make things simple, and then we're using the standard fair temperature, yeah, from the Eurocode. So this is a formula for the standard fair temperature. We do that in the spreadsheet, and then we can directly import into the ANSYS. Yeah, and then we apply into the ANSYS. For everyone know structural fire design, we know that there are certain degree of degradation for the materials because the steel member material in the high temperature is strength will degrade. So you have to using the degradation models. So this is the degradation model provided by the Eurocode 3 part 1, 2 for steel member. So that's what we use. So we also import into the ANSYS. And then after all the parameter, for sure you also need to define the thermal expansion coefficient, and then the so many factor you need to define. Then after you define everything, you just run a so-called multiphysics modeling. So what do we mean by multiphysics in ANSYS? So actually the so-called couple thermomechanical analysis. Yeah. So it's a combined steady state thermal and also static structural analysis. So in ANSYS we call that multiphysics. So the first stage is to perform a steady state thermal analysis with the input of the temperature, radiation, convection parameters here, and also the time history of them from the chosen fire scenarios. Yeah, but here we're using the standard fire temperature, but for sure you can using parametric fire temperature. And then after the analysis, because this is actually we run the heat transferring analysis, so we got the body temperature, or we call that member temperature. Yeah. So the member temperature result, the temperature for each structural member will automatically enter into the structural analysis module in ANSYS, yeah, as a structural load, yeah. So those temperature results will import as a load, and then the input data consists of the modular, yeah, as I said, modular elasticity, density, strength, strain relation, and also thermal expansion coefficient of the steel. So this is the process of how do we do that in ANSYS. So we need to first define a steady state thermal analysis step, and then followed by static structural analysis step, and then we can find out the result. So then how do we do that in ANSYS? So the modeling result discussion, we set up two models. One is the 3D model. I will show you later, yeah, because when I do the recording, the slides couldn't go back, yeah, so I have to tell you now. So we have the 3D model, and also we choose one frame. We also run the analysis, yeah. And what we found is the 3D global model is actually needed to have a clear understanding, because so the results show there are large difference between a 3D model and a 2D model. For instance, for the deformation, actually they show very large difference if you only model one piece of frame, and also if you model the whole frame. So the deformation is totally different. So that means for such complex structure, you can't just model one frame to represent the whole structure. You have to model the whole 3D frame to know the global behavior of this structure. Yeah. So this is the deformation shape for the 3D roof. And as I introduced, we also model one piece of frame. Yeah, so this is the deformation shape of single radial frame, because we want to know the difference between them. So this is a conclusion. So the conclusion is the multiphysics analysis of the whole structure behavior provides a more clear and accurate way in investigating the behavior of a space structure in fire. And then due to the complex geometry of space structure, it has dramatic different behavior compared to a single frame structure in fire condition. So therefore, simplified frame model may not provide accurate results. So that's what people normally do in the past. And also what we found next is that the space structure collapse due to excessive deformation at the center. Because there, if you see the previous deformation figures for 3D photo, you can see the huge deformation, excessive deformation at the center. So therefore, the center region of the space structure need to be protected, need to be fair protected. Yeah, so you can do a fair protection, either intramason painting or just try to delay the collapse of the truss. So yeah, that's what we found. So dynamic starting collapse at the center. So if we can protect the center, that will delay the collapse of the truss. So that the collapse mechanism we found is primarily starting from the center and then it propagates to the edge. Yeah, so that's my presentation. Yeah. And then thanks for your attention. So that's my email address. I work in University of London, and I hope I can have some chance to have some collaboration with you, because now we are doing the online conference, so we don't have much opportunity to talk to each other. So if you have seen my video, so this is my email address, so you can contact me so we can have some further collaborations. So thanks for your attention. Thank you.